class you talked about the reactivity. So you said that iodine was the most reactive, and then bromine, chlorine, fluorine. And
Yeah.
then you also said that alkyl halides are more reactive than aryl halides. So I
Yes.
think you showed the example with like phenol versus benzyl halides. So what if it's like which one affects the reactivity the most? Like what if
Well, that is
it's
that you don't need to worry about. So
okay,
basically, whatever you basically compare on the basis, assume the the organic part is same, then the iodide is going to be most reactive.
okay, so
If
we
the
won't.
yeah, if then next comparison, if the halide is same, then the alkyl will be more reactive than the vinyl or aromatic one.
So we won't get like a phenol, I don't know, iodide versus
Phenol, not
benzyl
called
group.
phenol,
Yeah.
phenol. Let's
Okay.
say,
Okay.
I want to ask you this question. Let's say I have this one, right?
Yeah. Versus the
And
iodine. Yeah. Yeah. Okay.
this one, okay? I won't ask you this question because, even myself, I don't cannot tell you based
Oh,
on the
okay.
principle we have learned so far.
Okay.
So I won't ask you compare these two guys.
Also for the why is it in like Grignard regions versus the lithium organolithium? Why is it that like in the product the halide stays when you use magnesium, but for lithium the halide does not end up in the product? Is there a reason?
Well, th- that is basically, first, the magnesium part, the magnesium has 2 units of positive charge, right?
Mm-hmm.
So you have one carbon anion connect to it, you still need something else.
Oh, okay. So the halide
Yeah,
stays.
yeah, because lithium is a single charged.
Got it.
Yeah.
Thank you.
Okay. Okay. Anyway, so I'm just gonna give you a brief summary what we learned in chapter 15. So chapter 15, we learned, the organometallic compound. So first, you need to know what definition organometallic compound. You need looking for the metal carbon bond. Then we look at the two most important organometallic compound. One is organic lithium, the other one is Grignard, X is halide, okay? And just for the simplification, make it easier for us to think mechanistically, we can consider both these two guys equivalent to carbon anion plus a metal cation, okay? So the organolithium and Grignard is basically a supply of carbon anion. And the metal cation part just spectator ions, they don't need to worry about. So this basically gives the two most important, the kind of reactivities of organolithium and Grignard. First, because carbon anion is super basic, that's why Grignard and organolithium, they are super basic. Second, because of the carbon anion also super nucleophilic, that also makes these two guys exceedingly good nucleophiles. So when you consider basicity of organolithium or Grignard, that makes it's important if you want to do Grignard or organolithium reactions, you have to avoid any the functional groups that has acidic the proton. Okay, so in the solvent or the environment should avoid any of those groups because all those groups has highly acidic protons. So those highly acidic protons will deactivate organolithium or Grignard. That's the most important thing. Okay, for the basicity. Then the nucleophilicity gives the those two kind of reagents ability to attack a carbonyl. And the kind of reaction we have learned that's the most important type of reaction is the carbon anion or organolithium or Grignard react with a carbonyl group. So XY, okay, and XY they are either hydrogen or hydrocarbon. Okay? So the reaction is usually done in two steps. First is in ether solvent. Second step is protonation. In the first step is the first step. Okay, the rate limiting step is the Grignard. Carbon anion attacks carbonyl carbon, and that give you the X, Y. I'm gonna draw a new one, so it's easier to see. That's what happens in the first step. And then second step, you add, the acid. The acid so that compound you got. Okay, if it's aldehyde, if it's a formaldehyde means both X, Y equal to hydrogen, you will get a primary alcohol as a product. If the one of these two guys, okay, is hydrogen, the other one is hydrocarbon, say like the one is hydrogen, this one say R, okay, R star, okay. So what you get is R, the R star HOH. You will get the secondary alcohol. If the both X and Y is the hydrocarbon group, you get tertiary alcohol. Okay, so that's the reaction about the organolithium and the Grignard. And in addition to organolithium and Grignard, we also going to look at the organocopper reagent. The kind of organocopper reagent we'll be looking at is called Gilman reagent. Okay. So how do we get a Gilman reagent? Usually we start copper 1 halide, and then take this copper 1 halide, react with an organolithium. So the first step, the organolithium react with copper 1 halide will give you LQ copper. Then LQ copper can react with another more of the organolithium, give you lithium di-LQ cuprate, and that is a Gilman reagent. So in this Gilman reagent, basically you have this lithium dicuprate as a real active, reactant, and the lithium mostly just the spectator ion. So because of this guy's negative charged anion, so the di-alkyl cuprate, they are nucleophilic. And the kind of reaction we will be learning about this Gilman reagent is a cross-coupling reaction. So the nucleophilic di-alkyl cuprate, it's capable to react with the organic halide as the electrophile. And this organic halide does not necessarily limit to alkyl halide, but alkyl halide does work. And in the reaction, basically the lithium di-alkyl cuprate will utilize one of these organol group and couple with the organol group on the halide and give you a hydrocarbon product. And this reaction is called cross-coupling reaction. It's basically, you see, take one of R group from the Gilman reagent and couple with another, the R group on the organic halide. So this type of reaction called cross coupled. And there's a certain, limitation on what kind of, hydrocarbons can be prepared by this reaction. So it is required that the R group on the dialkyl cuprate and the halide cannot be secondary or tertiary alkyl group. What happens if you have secondary? Okay, either this one is secondary or tertiary alkyl group, or this one is secondary or tertiary alkyl group. In that case, you will have the competing elimination reaction. So this kind of limitation is somewhat similar, but not exactly the same. Similar to the reaction we learned, I think, in chapter 6, the nucleophilic substitution reaction. Oh, no, not. I think it's a later chapter, basically, when we talk about elimination reaction. Say when you have an alkyl halide and a nucleophile, these two guys react. The reaction could go along two different pathways. One is nucleophilic substitution. The other one, the elimination. And which reaction will be preferred depend on what kind of electrophile used, mostly relate to the state hingings of the electrophile, but also relate to the the nucleophile. If you have if the electrophile is tertiary alkyl halide, you always see elimination. If it's secondary alkyl halide, that depends on what kind of nucleophile you use. If you use a highly basic nucleophile, then you're gonna see elimination. And if you have a highly nucleophilic nucleophile, then you see the substitution. It's somewhat similar here. If you want to avoid elimination, you have to avoid the secondary or tertiary alkyl group in both the Gilman reagent and the halide. So then if you are thinking about the using Gilman reagent or cross coupling to prepare hydrocarbons. So let me just give you a few the possible the combinations. Let me tell you one only one of them will work. Okay, so tell me which one is. So just for the sake of clarity, I'm gonna label the the point of connection in different the point of connection bond is in different color. Okay, so green bond means the point of connection. Okay, so which set will give you cross-coupling product at good yield, ABCD. Only one of them will give you good yield. So keep in mind, we have to avoid tertiary or secondary LQ group in both the Gilman reagent and the halide. So if you look at the 4 examples, here the Gilman reagent we have primary LQ group, sounds good. Here secondary LQ group with Gilman reagent, so it doesn't work. Here we have a secondary LQ group in the organic halide, doesn't work. Here we have a tertiary, the LQ group in the Gilman reagent. So only A works. Okay. So that's basically it's needed for you to avoid elimination. Okay. And the working, the other than the avoid, secondary and the tertiary LQ group, the rest of combinations all work. You could have, both the methyl or primary LQ group in the Gilman and the halide. It works. Basically, the one methyl group will combine with this Dodicil group, give you a product of 11 carbons. And here again, we have this butyl group, also can combine cross-couple with the phenyl group, give you a aromatic, hydrocarbon. And here you have, the phenyl group in the Gilman reagent part also can combine with this 8 carbons octal group in the primary halide, also work. And here is basically the example. You have a primary LQ group in the Gilman reagent combined with a vinyl halide in the the electrophile side, also works. Okay. And the reaction typically also the solvent, generally use ether solvent, diether ether, the THF, or it all work. And when you have a vinyl halide as the electrophile, the stereochemistry in the CC double bond is retained. Why not B? Because B, I believe I placed, one of them is secondary. I don't recall which one because the screen already gone. The alcohol, one of them is secondary. Okay. Now the trend in terms of how the reaction rate vary with the halide is similar with the what we have seen so far. Means the iodide is the most reactive, fluoride least reactive. If you're using alkyl halide as the electrophile, you also have the inversion of configuration. So suggests that the reaction might be something similar to SN2. And but because sp2 and sp organohalides also react, so SN2 is unlikely. And to be honest, the exact mechanism of this reaction still is a subject of debating. Okay? So but the current major opinion is that the reaction following the addition elimination mechanism. So basically, what happens in the first step is you have a Gilman reagent, then the LQ halide will be added on top. Both the LQ group and the halide group will be added to the copper atom, give you a intermediate will couple bound to the four groups. It's called the tetra-coordinated couple. And because of both copper and the carbon has higher electronegativity than copper. Well, both carbon and halogen, they have higher electronegativity than copper. So in this step, you see the oxidation state of copper increase. So this step we call the oxidative addition step. Then in the second step, let's say one of the two organic groups on the copper, they combine, basically release the hydrocarbon. At the same time, you will get another kind of you get LQ copper halide as a product. So in this step, the oxidation state of copper increase. And actually, you also can look at basically you are eliminating, the two groups from this intermediate. So this step called reductive elimination. So well, this is, I'm not gonna require you to know the details of this mechanism, but just give you an idea that what most likely the cross-coupling mechanism might be, because of although you see this halide, the reactivity trend and the inversion of configuration, but because of both sp2 and sp organohalide react, so it's not exactly SN2. So the current major opinion is just the addition, then elimination. This kind of this mechanism has certain in certain way is kind of similar to the electrophilic aromatic substitution and nucleophilic aromatic substitution. In both those reactions, we know there's addition elimination mechanism. I think that's what I would like to cover for the chapter the 15.